Hello guys, welcome back to my channel, and in this video I would like to discuss a more general property of the Laplace transform when it comes to integration. And like my previous video, I'm going to prove that property, and I'm also going to solve an example integral with that property. So let's get started. I'm sure you'll learn something new today. So the general property that I want to talk about in this video is basically the integral from 0 to infinity of, say, a function of a variable, say t, divided by t to the nth power dt, where n is any integer, is equal to the limit as s tends to 0 of the integral from s to infinity of 1 over n minus 1 factorial times the Laplace transform of the n minus 1th derivative with respect to t naturally of f of t, and integrated with respect to s, because now we are assuming that this Laplace transform is with respect to s, so the output function that you will get will be a function of s. That's why we have a ds here. Okay, so this is roughly what the property says, and let's go ahead and prove this. I'm going to use a fresh page to do that. See you there. So before starting the proof, I would urge you to look at some cases of the Laplace transform. Say you have a function uh, f of t. You have a function f of t. Basically, the Laplace transform of f of t with respect to s. I mean, in this proof, the Laplace transform is going to always be with respect to s. So Laplace transform of f of t is defined as the integral from 0 to infinity of e raised to minus st times f of t dt, right? But what about the Laplace transform of, say, f prime of t, so the first derivative of f of t with respect to t? That's going to be integral from 0 to infinity of e raised to minus st times f prime of t dt. And we can actually simplify this further. We can use integration by parts. So we can call this I, the part we want to integrate, because integrating f prime is just going to give us f back again. And we want to differentiate this part. So when we go ahead and do that, we have e raised to minus st times f of t evaluated from 0 to infinity minus, and this, the antiderivative of this is also a minus, so we have a plus integral from 0 to infinity of when we integrate this, we basically bring an s in the denominator. So yeah, I'm sorry, it's we're not integrating that, we're differentiating it. So we need to bring an s, and the negative got cancelled with the original negative, because the derivative of e raised to negative st has a negative in it. So we just have an s and e raised to negative st times f of t dt. So at infinity you have something like f of t divided by e raised to st at, say, the upper bound in the limit as t goes to infinity, minus something like uh, say f of t over e raised to st in the limit as t goes to 0, and this is just s times the Laplace transform of f of t. So in the limit as t goes to infinity, we don't care what function we have, this is always going to tend to 0. because the exponential in the denominator is going to grow really fast, and as t goes to infinity, if the denominator grows really fast, the entire fraction goes to 0. And we can also assume that because at when as t tends to 0, e raised to 0 is 1, so this goes to 1, and then we can assume that for now in this proof rather, that limit as t goes to 0 of f of t is 0. Let's just assume that. So we just end up with, so all of this will go to 0. We just end up with s times the Laplace transform of f of t. And I mean, this is a reasonable assumption because this integral is converging. So if you take the ratio of, so the limit as t goes to 0 of f of t over t to the n, this can't be undefined. This has to be equal to some constant, and that constant is equal to a. So that's basically one of the special properties of selecting f of t. And that's not all. We have to extend this assumption further, because this was just Laplace transform of f prime of t. Say we have the Laplace transform of f double prime of t. So by definition, integral from 0 to infinity of e raised to minus st times f double prime of t dt. Again, we have to integrate this. So we just end up with f prime of t times e raised to minus st evaluated from 0 to infinity, minus minus plus s times integral from 0 to infinity of e raised to minus st times f prime of t dt. And then we can say that f prime of t over e raised to st in the limit as t goes to infinity will go to 0, because we have an exponential in the denominator, minus the limit as t goes to 0 of f prime of t over e raised to st. Well, the denominator will go to 1, and we have to again assume that f prime of t as t approaches 0 will be 0, because again this was our condition, right? This has to equal the some constant, which in our case we conveniently define 0, because if you keep taking the L'Hopital's rule, if you keep taking the derivative of both the numerator and denominator by L'Hopital's rule, because we assumed that uh, in the limit as t goes to 0, f of t goes to 0, so we have a 0 over 0, so we naturally have to take L'Hopital's rule into consideration. F prime of t over n times t to the n minus 1 should also be 0 if this original thing is equal to 0 by L'Hopital's rule. In the limit as t goes to 0, this thing should also be 0. So, and this will follow for all derivatives. Say maximum you can take is n derivatives, so this will follow for, say, n derivatives of f of t. That is one assumption that is going to win us this entire proof. So everything became 0, and this is just the Laplace transform of f prime of t, with which we just calculated over here, to be s times Laplace transform of f of t. So this will become s times s, which is s squared times the Laplace transform of f of t. That's the value of the Laplace transform of f double prime of t. So the second derivative with respect to t of f of t is s squared times the Laplace transform of f of t. Well, we can see a pattern, and then we can generalize directly for, say, n minus 1th derivative of f of t. Again, as I said, that's why I said this assumption is going to hold for n derivatives of f of t. So why can't it hold for n minus 1th derivative of f of t? So that's why this holds, and all these other terms that we had to evaluate without the integral sign, all become 0, and we are left with s to the n minus 1 times the Laplace transform of f of t. That's basically the value of this n minus 1th derivative of f of t, the Laplace transform of that. This is the value of that. So now, why don't we integrate both sides with respect to s? Because as I said, this Laplace transform is with respect to s. So in the end, you're going to end up with another function, capital F of s. So we have everything of which is a function of s on both sides. So why can't we integrate from 0 to infinity ds on both sides? So when we do that, look at the right hand side. We have integral from 0 to infinity of s to the n minus 1 times the Laplace transform of f of t ds. And now I would like to use a property that I proved in my last video, which said that if you have, say, integral from 0 to infinity of a product of two functions dx, you can write this as integral from 0 to infinity of the Laplace transform of, say, one function times the inverse Laplace transform of the other function dx. So we can apply the same property here, and notice that it will be much more convenient to take the inverse Laplace transform of this function and the Laplace transform of this function. So when we do that, we just have um, integral from 0 to infinity of the Laplace transform of s to the n minus 1th power times the inverse Laplace transform of the Laplace transform of f of t ds. Now, to find the Laplace transform of this, recall one interesting property that we derived. So say we had the Laplace transform of t to the nth power. This was just gamma of n minus 1 divided by s to the n minus 1th power. So we can apply that here. And one condition of using this property was, say you started with x. After taking the Laplace transform and the inverse Laplace transform, you again write whatever values of s or t that you would have naturally got in terms of x again. That was one condition of using this. So whatever we obtain, we have to write in terms of s because that's the variable of integration. So this is just integral from 0 to infinity. In the place of n, we have n minus 1. Oh, I made a little error. This is a plus. I'm so sorry about that. So when we make substitution as n equal n minus 1 over here, we just end up with gamma of n divided by, we start with s, we end with s because of this, s to the n, and Laplace, inverse Laplace of Laplace is just original function itself. By definition, they cancel out. And since we have to end in s, so this will not be a function of t, it will be a function of s ds. And the gamma of n is a constant, so we can take it out of the integral. We have the integral from 0 to infinity of f of s divided by s to the n ds. Now what is this equal to? Well, let's look at the left hand side again. Left hand side was basically integral from 0 to infinity of the Laplace transform of the n minus 1th derivative of f of t ds, right? Yeah, ds. It was ds. And this is now equal to, we just calculated everything, gamma of n times integral from 0 to infinity of f of s divided by s to the n ds. We can divide both sides by gamma of n. So we have 1 over gamma of n times integral from 0 to infinity of the Laplace transform of n minus 1th derivative of f of t ds is equal to, now we can make a change of variable. We can change s to t, and ds is equal to dt. Upper and lower bounds remain the same. Integral from 0 to infinity of f of t divided by t to the n dt. And what is gamma of n? Just n minus 1 factorial, right? So finally, we have integral from 0 to infinity of f of t divided by t to the n dt just equal to 1 over n minus 1 factorial, and we can write this in a limit form such that limit as s tends to 0 of integral from s to infinity of the Laplace transform of n minus 1th derivative of f of t integrated with respect to s. And that, there you have it. We've proved our general theorem. Isn't that nice? It was a really nice proof if you ask me. Really short and sweet one. Now, it's actually time to apply this property. So say we have an integral, let's call it I, from 0 to infinity of sine to the fourth of x divided by x cubed dx. So according to our property, our f of x here, not t, doesn't matter what variable we have, is sine to the fourth of x, and our n is equal to 3. So our property is going to say that I is nothing but 1 over 3 minus 1 factorial times the limit as s goes to 0 of integral from s to infinity of the Laplace transform of n minus 1th derivative of f of x, which is sine to the fourth of x ds. So now we actually have to find n minus 1 is 3 minus 1 here. So the second derivative, 3 minus 1 is 2. So the second derivative of sine to the fourth. But let's simplify this first. Sine to the fourth of x is nothing but sine squared of x, the whole thing squared. And by trigonometric identities, sine squared of x can be written as, in terms of double angles, 1 minus cosine of 2x over 2, but the whole thing squared. We can pull the 1 over 2 outside. This becomes 1 over 2 squared, which is 1 over 4 times then the square of the inner part. So 1 minus 2 times cosine of 2x minus, rather plus, cosine squared of 2x. And we have 1 over 4 minus 1 over 2 times cosine of 2x, and 1 over 4. We can write cosine squared again as in terms of these double angle formulas. So we have 1 plus cosine of 4x divided by 2, 1 over 4 minus half cosine of 2x plus 1 over 8 here, 1 over 8 plus cosine of 4x divided by 8. So it's time to take the first derivative now of f of x. We have to take two derivatives. So anyways, the constants will go away to 0. Sorry, 1 over 4 and 1 over 8, not this half, will go to 0. The derivative of negative half cosine of 2x is going to be minus half times minus 2 times sine of 2x. And when it comes to differentiating this, we have minus 1 over 8 times 4 times the sine of 4x. Negatives will cancel, the 2's will and half will cancel. We have sine of 2x minus half of sine of 4x. Now let's take the derivative again. So the second derivative of f of x with respect to x is going to be 2 times cosine of 2x minus 2 times cosine of 4x. Well, now we can easily take the Laplace transform. We have the second derivative, we have this term. Let's take the Laplace transform of that. So the Laplace transform of the second derivative of f of x is going to be, I'm directly writing the formula because the cosine of, say, Laplace transform of a cosine function, say cosine of 80 is just s over s squared plus a squared. So I'm directly writing that. So we have 2x divided by x squared plus 2 squared, which is 4, minus 2x divided by x squared plus 4 squared, which is 16. That's Laplace transform, and then we have to integrate that still. So our I is nothing but, if you go up ahead, 1 over 2 factorial, 1 over 2 factorial times the limit as s tends to 0 of integral from s to infinity of, we found out the Laplace transform part. So 2x divided by x squared plus 4 minus 2x divided by x squared plus 16. Actually, we should write this as an s because the integral was with respect to s. Yeah, ds. 1 over 2 factorial is 1 over 2. We can write this, we can just apply the limit, integral from 0 to infinity, of 2s over s squared plus 4 minus 2s over s squared plus 16 ds. Integrating this is easy. We have a natural log basically. So half of natural log of s squared plus 4 minus natural log of s squared plus 16 evaluated from 0 to infinity. This is half of the natural log of s squared plus 4 divided by s squared plus 16 evaluated from 0 to infinity. So at infinity, the limit as s tends to infinity, everything will become 1 because the leading coefficients of these dominating term is 1. So we have 1 over 1, which is natural log of 1 is 0, minus half of when you plug in 0 in place of s, you have natural log of 4 over 16. You can suck up the negative and flip the arguments. You have I is basically equal to the half of the natural log of 16 divided by 4, which is equal to half of natural log of 4, which if you want to apply some properties of exponents, is 4 to the half power, which is square root of 4. Taking the positive branch, because this natural log is real, you can't have a negative inside here. You have natural log of 2. That's basically equal to I, which is equal to integral from 0 to infinity of sine to the 4th of x divided by x cubed dx. So notice how powerful this technique is. I mean, all the integrals that we struggle to calculate, by regular techniques, this would have been really hard by regular techniques. We can do easily by this general Laplace transform property. So that's it for this video. I hope you learned a lot. So I really hope you like this video, guys. Please like, share and subscribe to my channel. I want more subscribers. I want to reach at least 100 first. You can follow me on Instagram. I have this username gamma underscore die gamma. And please recommend me to all your friends. Stay home, stay safe, have a great day. Peace out.